Welcome everyone to our weekly event, and just wanted to mention that we are still finalizing the list of speakers for the annual BHI conference in the middle of May, and a solicitation of additional names was sent to the postdocs. The postdocs are in charge, so please send any suggestions you have to either Paul Chesler or Fabio Porcucci. They are the two that coordinate this. And other than that, I must say that I was pleasantly surprised to meet someone from the past. When I came to Harvard, I taught a class, Introduction to Astronomy, and apparently one of the students that was in the class is giving a talk here today. So I'm happy to hear that the experience of attending the class was not too damaging to your intellectual growth. So who is making the presentations today? Go ahead.
So our first speaker is Peter Hintz. He's an assistant prof down the road at MIT, also a Clay Fellow. He's going to be speaking to us about strong cosmic censorship.
Thank you very much, and thanks for the invitation to speak. Is there actually like a clicker thingy, or I'm just going to do the thing here. It's whole hand. Yeah, that works. Handlock and Windows. All right. Yeah. So thanks for having me here. I've been here once before 2 years ago. I hope that hasn't been detrimental to your growth. Okay. So, but I'm talking about something quite different now. So this recent developments in strong cosmic censorship, it seems like in a few weeks there is going to be a somewhat philosophy-oriented talk that sounded in the abstract like it could be in a somewhat similar direction about determinism and relativity. So this is going to be a completely classical relativity talk, but in the spirit of keeping it for a general audience, let's start very simple with the wave equation for a one-dimensional, say, vibrating string. X is the coordinate along the string, and t is time. And so the equation that is satisfied by the amplitude of this string is the wave equation, so written there, minus second time derivative plus second space derivative of v is equal to 0. And in order to determine the amplitude uniquely, you have to specify two pieces of data, the initial amplitude, v0, and the initial velocity of each point of the string, v1. So these are the so-called Cauchy data, and we're imposing these Cauchy data at this Cauchy surface, sigma, which is time equals 0. And a salient feature of solutions of the wave equation is the finite speed of propagation. And so if the initial amplitude and velocity are non-zero only in this indicated blue region here, then this initial perturbation is going to spread at most at the speed of light or sound or whatever the physical system actually is, which in this case is equal to 1, no units here. Okay, so support signal spread at the speed of light at most. Okay, so we can turn this picture around a little bit and do the following thought experiment. So suppose we're again looking at the wave equation, but we only have limited knowledge of the Cauchy data. So suppose we only know the Cauchy data in this finite blue region here, where say x is bounded by some fixed number. And let's try to solve the wave equation then. Well, turns out that the solution is unique exactly in the interior of this black big triangle. And it's easy to see why that would be, because if you look at a point P inside of that triangle, well, all the pieces of initial data that could affect the amplitude of the wave at P must come from the base of this green triangle here, because anything that happens, any amplitude that's somehow out here cannot actually reach the point P because of the finite speed of propagation. On the other hand, the point Q outside of this triangle, you cannot determine the amplitude of the wave given your limited knowledge, because it could be that there is something out here in the red region, some initial perturbation, that travels towards Q and affects the value of the amplitude of the wave there. Okay, so red is the missing piece of information that disallows you to determine the amplitude of the wave at Q. And the Cauchy horizon associated with this restricted surface sigma is exactly the boundary of the region where the amplitude is uniquely determined by initial data and where it's not. Okay, so that's the Cauchy horizon. Of course, it's a very artificial scenario here, because we just artificially made our initial knowledge smaller. But we'll see next that on certain black hole spacetimes, a Cauchy horizon appears very naturally without such artificial restrictions. Okay, so feel free to interrupt me at any point if something's unclear. Okay, so let's walk towards the Cauchy horizon of charged black holes, and the model that I'll talk about here is the Reisner-Nordström black hole spacetime, which is a particular solution of the Einstein-Maxwell system. So it describes gravity coupled to electromagnetism. So here, for your amusement, is the schematic form of the equation. So you have the metric tensor G and an electromagnetic field F. And it's a two-parameter family of spacetimes depending on the mass of the black hole, which is some positive number, and its electric charge, which I'll take to be non-zero, so positive, and it has to be bounded by some maximum extremal value. So without units, Q is between 0 and M. The spacetime has very simple topology, and the metric is also explicit. I'm just writing this down, not so you can actually memorize it, but just to demonstrate that it's indeed a very simple and in fact the unique spherically symmetric solution of the Einstein-Maxwell system, which then ends up having these two parameters, mass and charge. So it's a very natural object, nothing arcane. Okay, so what's the geometry of such a spacetime? And here's the Penrose diagram. So the main feature of the Penrose diagram, so first of all, it's just two-dimensional. I dropped the two spherical directions, spherical symmetric spacetime. So they're gone, and I only plot basically the R direction, which is some of the distance from the center of the black hole, if you like, and the time direction, which, okay, but the feature of this here is that obviously the R coordinate is not actually linear, but it somehow starts at 0, increases, and goes all the way to infinity over here. The feature of the Penrose diagram is that future-directed causal observers move upwards at an angle at most 45 degrees to the vertical. And light that travels sort of in a radial direction, so radially away from the black hole into the black hole, travels at exactly 45 degrees. Okay, so 45 degrees is somehow where you can move. Okay, and it turns out that there are two values of the radius function, r minus and r plus, having some certain values, which are horizons for this black hole spacetime. So the event horizon is at some particular value of the radius, and it has the property that if an observer A travels, as indicated, from the black hole exterior region, which is sort of far away from the black hole where we would like to be, crosses the event horizon, then at that place where A is written here, A can try to decide to go back to the black hole exterior, but will not be able to, because A can only go at most 45 degrees upwards. But this here, the event horizon is exactly at 45 degrees. That's the causal structure of the spacetime. So A cannot actually cross back from region 2 into region 1. So that's what is an event horizon, obviously. Once you cross it, you cannot come back. Okay, and then A can in fact travel further on, cross another, which will turn out to be a Cauchy horizon, into region 3, which I don't think actually has a commonly accepted name. And the singularity of the black hole would be sitting at r equals 0, so A can actually avoid it altogether if A is clever enough. But okay, so this is somehow the quite bizarre Penrose diagram of such a black hole spacetime. But also say that null infinity here, which is, as I said, very far away from the black hole, this is where somehow radiation would be emitted towards, and this is where we have our gravitational wave detectors. Okay, so let's focus on what's disconcerting about the spacetime. Namely, it has a Cauchy horizon in the following much more serious sense than my silly initial example. Okay, so suppose that you're considering the evolution of a wave, a scalar wave, electromagnetic waves, gravitational waves on this spacetime, and suppose observer A was somehow told the complete initial conditions, the complete Cauchy data, on the surface sigma down here. Okay, so A can then plug these data into her computer and compute what the amplitude of the evolving wave is. However, as soon as A crosses this thick red region along the Cauchy horizon, A will no longer be able to predict, purely within classical field theory, the amplitudes of the waves that are propagating, say electromagnetic waves for the sake of definiteness. And why is that? Well, once you're at a point beyond, like in region 3, and you look at the backwards light cone, so what signal, like what information could affect the amplitude of your electromagnetic wave, well, there's a piece missing that somehow comes from the singularity somehow. Well, you cannot, it's no longer certainly uniquely determined by the initial data on the surface sigma. There's still this artificial Cauchy horizon out here in dotted red, but that can be pushed away if you just increase the surface sigma towards the left. But the Cauchy horizon here, the red thick line, is really a geometric feature of the spacetime. Okay, and in fact, this observer A crosses this Cauchy horizon in finite proper time, and reaches, therefore, in finite proper time a region where A cannot anymore uniquely predict the amplitude of the propagating wave. Okay, so that's that's quite disconcerting, because then as soon as you have complete knowledge of the initial condition, but then in finite time you cannot predict anymore what's going to happen. It's not a problem of probabilities or anything. It's purely classical field theory. Okay, and here's the proposed resolution of this sort of philosophical problem proposed by Simpson and Penrose in the 70s. And the idea is that, so you consider this observer A crossing the Cauchy horizon in finite time, but in any realistic space-time, of course, there's going to be radiation falling into the black hole. And so this is here in this cartoon depicted as an observer B that stays outside of the black hole. And in fact, the timeline of this observer B has infinite proper time. So B lives forever. And in this picture, B just sends a constant frequency wave into the interior of the black hole. And if you want to somehow have it discrete, you just turn on the laser pointer once a second. So that's what B does, free laser pointer. And in this Penrose diagram, it looks like they're closer and closer together. But as measured in B's proper time, they're always 1 second apart. Okay, so B lives forever, but A crosses the Cauchy horizon in finite proper time. So therefore, A receives in a finite amount of time the infinite number of signals sent in from the observer B. And so in frequency language, somehow the signal that A receives from B is blue shifted more and more and more as A approaches the Cauchy horizon. And in fact, it's infinitely blue shifted by the time A is at the Cauchy horizon. So the idea is then, of course, that B just sends in something fairly mild, but A gets destroyed by like some ultraviolet catastrophe, some singularity. The field, electromagnetic field, let's say, will become singular in some sense that need to make precise.
So the metric will change, and therefore this Penrose diagram should be different.
Right. So this is so they actually did the toy model for just linear wave propagating, electromagnetism propagating on the spacetime. But then in reality, what you would like to understand is the evolution of the actual Einstein field equation. And then in the linearized regime, well, of course, nothing ever really happens because the underlying spacetime is what you're perturbing. But in the nonlinear regime, you then expect that indeed this concentration of energy at this Cauchy horizon will cause a singularity of the actual spacetime metric. And ideally, I mean, unfortunately for A, but ideally for determinism, you expect or hope that this singularity will be terminal in the sense of infinite tidal forces or something that you need to, again, decide on how you define terminal. I'll get to that in a little bit. Right, so this, exactly. So this is indeed what then Penrose's strong cosmic censorship conjecture states in this particular context, namely the maximal globally hyperbolic development. So think of this as the largest domain of unique existence for a solution of the initial value problem for the Einstein equation. So this largest space-time region where you can uniquely predict what you will measure given complete knowledge of your initial data on sigma. So this domain for generic initial data is inextendible as a suitably regular Lorentzian manifold. So there are some things that need to specify. So what does it mean to be generic? That's a math question more than perhaps a physics question. Is it measure, full measure, or bare category sense, something? Suitably regular, you have to decide, is the infinitude of some curvature quantity, some of the determining feature, or is it some infinitude of some energy quantity? So that you have to decide. Yes. But the reason why the word generic is there is clear from the picture. Namely, I just told you, you have to believe me, that this is the Penrose diagram of Rice and Nordstrom. And in fact, the metric is regular, smooth, analytic across the Cauchy horizon. But it's a very special space-time because there's no radiation in there. It's a stationary space-time. But as soon as you perturb the initial data ever so slightly, then you will have actual dynamics in the exterior, and actual waves will propagate outwards null infinity for us to measure, propagate into the black hole to cause doom for observer A and cause the singularity at the Cauchy horizon. So that's the idea behind this conjecture. All right, so now there are some rigorous results that prove or disprove this in various versions of the word singular. The first result was due to Jonathan Luke and Sung-Jin Oh a few years ago. And they consider exactly this simplest toy model of the scalar linear wave equation. So box phi equals 0, so box is like the minus second time derivative plus second space derivative, but now in the geometric sense for the Lorentzian spacetime. And they proved that for generic Cauchy data, phi0 and phi1 on this initial surface, the solution phi, in fact, does not lie in energy space, H1 it's called, near any point on the future Cauchy horizon. So somehow you're supposed to think that indeed the energy as measured by an observer crossing the Cauchy horizon, attempting to cross the Cauchy horizon, is infinite at the Cauchy horizon at any point along the Cauchy horizon. The exact statement is slightly more precise about the energy of the wave on any space-like hypersurface that is transversal to the Cauchy horizon. Okay, so in other words, waves do have infinite energy across the Cauchy horizon, generically. But in fact, it's a slightly older theorem by Franz and myself that solutions do remain bounded and continuous up to the Cauchy horizon. So it's a quite subtle question. So the amplitudes remain bounded, but somehow the derivative of the amplitude becomes infinite, roughly speaking. Okay, so this is the linear story, and there are many more refined works. So the Rice-Nordström spacetime is perhaps somewhat artificial because no black hole is actually really charged. But rotating black holes are. And so that's the Kerr solution. And in fact, again, scalar linear waves remain bounded up to the Cauchy horizon of a rotating Kerr black hole. They have infinite energy, which is a result by Luke and Swirsky, upon assuming certain quantitative decay rates in the exterior of the black hole. I'll get to back to that in a second. And regarding the nonlinear problem for the Einstein equation, there's a recent result by Pheromones Luke, where they proved that the metric indeed remains continuous and bounded up to the Cauchy horizon. However, generically, the metric will have a singularity on the level of C2. So that means two derivatives of the metric go up generically, which means which is an indication of a curvature singularity. But this latter result is in a spherically symmetric model system, Einstein-Maxwell scalar field. The first one is in the full no symmetries assumed vacuum setting. So this is the state of affairs for the nonlinear problem. So, yeah. So
this is all sub-extremal?
Yes, it's all sub-extremal. So in fact, there's work by Gajic on so I know about the scalar wave equation for the extremal case, I think extremal Rice-Nordström, where actually energy does remain bounded up to the Cauchy horizon. So it seems like an intriguing difference again between sub-extremal and extremal. Okay, so I mentioned that some of these results were conditional upon certain decay rates of perturbations in the black hole exterior. For instance, the nonlinear stability or some quantitative decay bounds for the scalar wave. And so let's just look at this again in a bit more detail. So in this picture that I had before, what really happens is that B doesn't send in a fixed amplitude wave every second, but that in a physically realistic system, there's going to be perturbations, electromagnetic, gravitational, propagating the spacetime, but they will escape towards null infinity for us to measure. They will escape into the black hole. But at any fixed region outside the black hole, energy will decay in time. And typically on these kinds of spacetimes, Minkowski space, Schwarzschild, Rice-Nordström, Kerr, the decay rate of waves is typically inverse polynomial. For scalar waves, it's a lot of works by, so also for gravitational waves, electromagnetic waves, it's been proved by a lot of authors over the years. But if you then reconsider this blue shift effect, as I explained it, well, then you have a competition, right? Because the waves falling in have decreasing amplitude as measured by A, and then they get amplified through this geometric effect at the Cauchy horizon. So the question is, which one wins? If the decay of waves in the exterior is so fast that the scrunching up here near the Cauchy horizon does very little to actually increase energy there, it might well be that A does not get annihilated by some terminal singularity. Whereas if the decay is too slow, then the blue shift effect, so the scrunching up, will win. Okay, but on these asymptotically flat spacetimes that I just mentioned, decay is typically inverse polynomial, and it turns out that you always expect the decay to be too weak to counteract this emergence of the singularity at the Cauchy horizon. What I would like to point out, however, is that this explanation also shows you that the question of what regularity you have at this inner horizon, and therefore whether you, let's not jump ahead of myself, that the regularity that you expect at the Cauchy horizon actually depends on large or infinite timescales of the propagation of waves in the exterior of the black hole. But as soon as you talk about having to understand very long or infinite timescales, you also have to worry about very large spatial scales. At which point, of course, the value of the cosmological constant will start playing a role. Yeah.
What are the details of the interactions that A would be having with this field of energy that's near the Cauchy horizon? Could it be scattered into the Cauchy horizon by this? I mean, I don't.
It could, but let me actually go to the 2 slides ahead. So H1 is the regularity that I mentioned in these Troy model results, and the reason why this is actually the interesting level of regularity is that if the scalar field is in H1, and you can generalize this to the metric case as well, that's the minimum requirement you need to have in order to make sense of the Einstein equation in some weak sense. So as soon as the solution of for instance, as soon as the scalar field in a coupled Einstein scalar field system has regularity H1 or better, you can actually try to extend the solution of the Einstein, look at this picture, you can try to extend the solution of your Einstein scalar field system beyond the Cauchy horizon, because the Einstein equation still makes sense as an equation distributionally. And you can extend the solution in non-unique ways, and so then A would be in trouble, some determinism would be in trouble because A can travel into a region where the Einstein equation still is well defined, but A cannot predict anymore what you will measure. Whereas if the regularity is below H1, then there's no way even to make something like you suggested, scattering into the beyond the Cauchy horizon, to even make sense of this, because the Einstein equation is no longer cannot be made sense of in any sense.
And we just decide to choose how regular we want these to satisfy.
On the mathematical side, it's somewhat the absolute limit. And some of these weak solutions are completely arcane. In fluid dynamics, for instance, weak solutions are required to describe things like shocks. But if you don't even have that notion of a solution anymore, then you give up and do something else. Of course, there's also a question, H1 might not be is probably not the correct regularity if you take quantum effects into account, but that's not for me to.
So that's what I was about to ask you, because even if there is no B, nobody is sending any waves, there are vacuum fluctuations that potentially could get, for example, if you have a charged field, that you can make pairs, you can make, out of vacuum fluctuations, you might actually grow the energy density.
That might happen, but
nobody did the calculation of that.
Not that I'm aware of,
okay.
I don't know the proper mathematical framework to prove theorems about that. But as far as I'm aware, these things have basically only been studied in the classical
I think there have been works on that.
Okay, yeah. Okay, so let me just quickly, in the last 5 minutes, talk about this large spatial scale version. And what I want to discuss really is the similar problem for spacetime with the cosmological constant positive, which makes the spacetime expand exponentially fast. And correspondingly, you might imagine that waves decay at a faster rate, not polynomially anymore, but exponentially. And that's something that I proved with Bashi a few years ago. So based on a lot of work of other people, Greenwich Observatory, Yaslov, and so on. And so the result is as stated here. If you have smooth initial data, then solutions of the wave equation, scalar wave equation, decay exponentially in time at a certain rate alpha. And as I just argued roughly, the regularity of waves near the Cauchy horizon is determined by the competition of the decay rate alpha and this geometric quantity that determines the focusing of incoming waves, which is the surface gravity of the Cauchy horizon, whatever that is, some positive number. And the regularity turns out to be 1/2 plus beta, at least. So you see exactly, the higher the decay rate is, the higher alpha, the more regularity you get. But the stronger the focusing is, so the stronger k is, the less regularity you get. So h1/2 plus little. So the question then becomes whether beta is 1/2 or less or more. And I'm just mentioning that we also proved black hole stability in this cosmological setting, which also provides exponentially k rates in the exterior of the black hole, even for the full nonlinear Einstein vacuum equation and Einstein Maxwell equation. So this the top theorem also works in the nonlinear setting. Okay, so I just already explained why this computation of beta is now some of the key thing we need to do. And in fact, there are results by Portuguese group around Costa, Natario Silva, that shows that in fact for the spherically symmetric Einstein-Maxwell scalar field system, you can in fact extend solutions of the system non-uniquely as weak solutions of the Einstein equation past the Cauchy horizon if beta is sufficiently big. So they prove 7/9. They say it should be 1/2, but it doesn't quite follow from their methods, but 1/2 should be indeed the exact borderline. Okay, and looking at this, I mean, so this result here is, it's just if beta is between such and such, then these kinds of things happen. But what is beta actually? And so the point is that one can actually compute beta numerically. And so how come? Well, it turns out that this exponential decay rate is exactly the spectral gap of the perturbation spectrum of the black hole. So quasi-normal mode spectrum, resonance spectrum, depending on who you ask. These are the names. And you can compute them numerically. So here's a rough sketch of what I mean by this. Well, it turns out that perturbations phi of the black hole, say gravitational, scalar, anything, can be expanded into a sum of damped harmonic oscillators with frequency, complex frequency Zj, and then some complex coefficients Pj, or spatial profiles Pj really. And these numbers Zj that appear in the exponent, these are the quasi-normal modes of the black hole. So they're the characteristic frequencies. They don't depend on the initial data. They only depend on the actual black hole metric. And here's a sketch of them. I mean, people have computed them in detail for a while. Cardoso, Berti, Starnetz had a long review article, for instance. And it turns out that all these perturbations decay at a minimum amount of e to the minus alpha t for some alpha, which is, you can just read off it's the smallest negative real part of any of the resonances. Okay, so you compute this quasi-normal mode spectrum, which is some certain eigenvalue problem for linearized perturbations. You get the number alpha out of it, you compute the quantity beta, and you can determine is it bigger than 1/2 or is it not. And so in this picture here, which I stole from the LIGO and Virgo first paper on black hole mergers. So here's the in-spiral, then eventually the black holes merge over here, and then this out of equilibrium single black hole settles down to its stationary state at an exponential rate with a certain oscillation frequency. So from this people have read off, I think with 10 or 20% accuracy, the real part of Zj corresponding to the decay rate and the imaginary part corresponding to the oscillation. So they actually get their hands on, say, the first one of these polynomial modes. Okay, and so this connection was first discussed in a paper in the 90s by Mellor and Moss, and then we revisited it in a paper a few years ago, and then Diaz-Real and Santos followed up and did the same thing for gravitational waves. And what we found is that there do exist parameters for Reisner and Nordstrom black holes in de Sitter space, positive cosmological constant, which are sub-extremal, such that in fact this ratio here is bigger than 1/2. So we proved this for scalar perturbations, and then the Cambridge group did this for electromagnetic and gravitational perturbations. In fact, it turns out that in the latter setting, you can make beta as large as you want in the sub-extremal regime, bigger than any of your favorite number. And so this indicates, certainly in this latter very extreme case where beta can be 10, that there should be no problem whatsoever in making sense of solutions non-uniquely across the Cauchy horizon, and also quantum effects, at least at the Cauchy horizon, wouldn't play a role because the spacetime is so regular there that probably no quantum effects plays a role. What you asked is somewhat independent of that last statement. So this indicates that in these spacetimes, strong cosmic censorship may well fail, and there are some constructions, as I said, of non-unique extensions.
Are all these cases near extremal though?
They're all near extreme, yes. And so there has also been follow-up work by the same authors, Diaz-Real and Santos and Eperon, where they study the Curtis Sitter case of fast rotation but no charge, and they find that beta is always less than 1/2, but as you reach extremality, it gets as close as you want. And there is still a chance that if you have a very fast rotating tiny charged black hole, that it might actually be above again. So it becomes a very solid question.
So this gravitational and electromagnetic perturbations, you said they can have an arbitrary large beta. This is all still a linear analysis?
This is linear analysis.
So what do you expect that happens if you go to second order in back reaction?
Well, so the work by the Pheromones and Luke that I mentioned here, so they assume that perturbations decay at a certain polynomial rate along the event horizon, and they have some, so they have a characteristic Cauchy problem. Though they haven't written it down in that way, but I'm pretty sure it's true if you just change their proof and add the cosmological constant, which doesn't really affect anything in the interior of the black hole. It just affects the asymptotics you have along the event horizon. Then their proof goes through and you get C0 solutions. But in fact, I would expect that you can do a more precise analysis with a stronger assumption and actually prove higher regularity of the metric. So I would assume that it indeed holds true also for the nonlinear case, but that's the conjecture of the view. Yeah, but I mean, one particular consequence of their work is that in fact the Cauchy horizon remains a null singularity. I mean, it might not be singular, but it probably is. But in fact, upon perturbation doesn't become even a space-like singularity, so I'm sure that Paul is not wrong with that. But yeah, okay. Sorry for running over time. Thank you very much.
Additional questions for Peter?
Perhaps a naive question. Do we know that if we can create these black holes, these are near extremal charged black holes, so if I have a regular distribution of charged matter in de Sitter space, do we know that we can collapse that matter and produce such a black hole that's near extremal?
So I'm not sure about rigorous results of that form, but yeah, so I'm not sure about the collapse.
So one way out would just be to say you're starting off with initial conditions which are not realized via a collapse problem.
Right, so if you start with the collapse problem and you have a little bit of scalar field left, it turns out there are still parameters for which this.
Yeah, but what I'm asking though is, can I collapse a regular distribution of matter and produce a near extremal black hole in a de Sitter space?
I don't know whether the answer is yes. I would suspect so, but yeah, I don't know of any good results of that form or numerical results. But I mean, again, some of this charged version is a fairly artificial case. It's allowed by the Einstein equations, but it's artificial. The rotating case is much more natural, and I suppose for that one, your question would definitely have a yes as an answer, even though again that's not proven either, but we observe it. Yeah.
Can I just ask to clarify for myself? You said that your Q is near extremal, so it's near M, and as Q becomes small, maybe things don't actually do work out, and beta is quite small.
Yes, so I don't have a picture on the USB stick now. I have it on my computer. But yeah, so it turns out, so if you have a positive cosmological constant, the extremal case, actually the extremal charge is a little bit above M, so you can have a little bit more charge because you have the exponential expansion of the universe with helping you out. Yeah, and it turns out that for as soon as you're away just a little bit from this extremal range, then this beta is less than a half, and you're in good shape. So all the actual very mildly charged black holes would be expected to.
Do you have a precise sense of where this transition occurs?
I mean, numerically, it's not a formula,
Sure,
but it's
okay.
Yeah. Anyway, there. So so if you increase the mass, then you have the charge here. And it turns out the diagram of subextremal Weiss-Nordstrom de Sitter space looks something like this. There's some maximal mass and charge here. And then it turns out that the regime where we see this violation is really, really tiny over here. It's really up there.
Okay. Any further questions? If not, let's thank Peter. Thank you.
How are you?
Yeah, I think I'm on PowerPoint. Okay, just go over here. Yes, there we go. Easy enough. Hi, I'm Matt Stanley. I'm a historian of science at NYU. Thanks for being here, and thanks for having me. I think the last time I was in this building was when I was the university registrar, and I was turning in the physical copy of my dissertation a very long time ago, so this is a much more pleasant atmosphere than having people measure my margins. So today I'm going to be talking about some material that's coming out of my recent book, Einstein's War. And it's about Einstein during World War I, but I think on a more important level, it's about how Einstein becomes a scientific icon, that is, how he becomes the sort of symbol of what it means to do science. And usually when we think about Einstein as an icon, we have either sort of the old wizard version that knows all the secrets of the universe, or the young heroic version that's battling against scientific dogmatism. But that's not actually neither of these are actually the moment when he becomes an icon. It's the middle-aged Einstein. His hair's just starting to turn gray. He's not really famous yet. This is the Einstein we need to think about at the beginning of World War I. He's done important work in physics, but he's certainly not famous, and most certainly not a household name like he'll be later. Right at the start of World War I, he takes up his position in Berlin, and so kind of for the first time, he's able to really focus on general relativity, which at this point in 1914 is still in what he calls the Entwurf stage, kind of the draft or the outline. He's got a lot of the theory together, but he's still having trouble with things like whether or not space-time is real and whether or not covariance is important. It's still a work in progress. But he doesn't have to teach, he doesn't have any administrative responsibilities, he can just sit down and calculate and think. So by November of 1915, he writes down the field equations. That's the end of his famous race with Hilbert. He presents the results to the Prussian Academy of Science. So this is really an extraordinary moment, right? This man will eventually be the most famous scientist of all time. This is his magnum opus. It's the theory that brought you all here today. And essentially no one knows about it. That is, if you were not in Berlin in November of 1915, you probably did not know that any of this was going on. And the reason for that is that 1915 is well into World War I. So Germany is under blockade, both land and sea, and the blockade is of course supposed to keep out things like armaments, but it also keeps out things like scientific papers. So Einstein literally cannot send the papers of general relativity out to other countries, and he can't get communications from other places. So the war begins impacting Einstein's work essentially immediately. Right at the beginning of he had hoped that soon after he got to Berlin, there would finally be an observational test of relativity. That's the gravitational deflection of light. You can only do this at a solar eclipse. Fortunately for him, there was one coming up in August of 1914 in Russia. Max Planck actually gets the funding to send an expedition, a group of German astronomers, to the Crimea to do the observation. Unfortunately, the war breaks out days before the eclipse, and the astronomers are all arrested as spies. So Einstein is very frustrated that he came close. It actually turns out to be good because Einstein was working with the wrong prediction of the deflection of light at the time. So if they'd actually carried out the measurement, that actually would have been really bad. Other things that were making things difficult for Einstein is that scientists on all sides of the war sort of go into their nationalist camps almost immediately. So very soon after the beginning of the war, a group of German intellectuals sign what comes to be called the Manifesto of '93. This includes essentially all of the important German physicists, people like Planck. And what this document does is declares the unity between the German army and the German scientific community. That is, anything that the German army does, scientists must necessarily approve of as well. As sort of the nature of the German culture. The response
It's
say...
becoming in the nature of the American culture also.
I'm sorry, well, that's the Americans don't appear in the story, but yes, we can go for that. So the French response to this is to throw all the German members out of the Academy of Sciences. The British response is similar. This argument begins to form in the British scientific community that there's something about the German character that means they can no longer do science. That is, they explicitly discuss the removal of Germans and German ideas from the international scientific community. This is all very painful for Einstein because he is a left-wing socialist. He believes in pacifism, he's an internationalist. He feels very strongly that nationalism is sort of the worst of all human diseases. And all of a sudden he finds himself in the grand imperial capital of Berlin, surrounded by all of his friends, people like Planck and Fritz Haber, who, as near as he can tell, have suddenly gone insane. And he has no one who he can talk to. And he really feels that science has to be the last redoubt of internationalism. But it makes it very difficult for him to think or do work. Another reason it becomes very difficult for him to do work is that he, like millions of other Germans, are starving due to the blockade. Einstein becomes seriously ill several times during the war. At one point, he's has life-threatening jaundice due to malnutrition. He's bedridden for a long period of time, and in fact, he writes the fundamental papers of relativistic cosmology in his pajamas in bed. So if you wanted to come talk to Einstein while he was sick, you had to come and sit on his bed and do the calculations with him. So he's got a lot of obstacles, but as he describes it, the most important obstacle to him getting his work done is this kind of political and social environment. He doesn't like being the only pacifist in Berlin, so he spends a lot of his time in the Netherlands, where he hangs out with this group here. The Netherlands are neutral during the war, so he can more or less go back and forth freely. So Paul Ehrenfest, Willem de Sitter, and Hendrik Lorentz. And Einstein likes that he can speak freely around them because they are all internationalists like him. He describes it as, I can take my muzzle off when I'm in the Netherlands. So Leiden, this little town in the Netherlands, essentially becomes the world center for general relativity research because that's the only place Einstein travels to. But again, no one really knows about it. De Sitter decides to do something about that, though. So he writes up a letter describing the new theory of relativity and sends it to the Royal Astronomical Society in London. Since Netherlands are neutral, he can send mail back and forth, even though Einstein can't directly. And it gets opened by this guy, who's, if you don't recognize him, Arthur Stanley Eddington. He's the secretary of the RAS at the time. And I can't overemphasize how lucky Einstein was that Eddington was the one who opened up this letter. And not just because he understood the mathematics that the theory was written in, but he was one of the very few British scientists who would have been willing to even think about a German theory at the time. And this may sound kind of hyperbolic, but I'm not exaggerating when the Royal Astronomical Society explicitly said that they would not allow German ideas to be discussed at the society. But Eddington is an internationalist. He makes sort of practical arguments that astronomers can't restrict themselves to national boundaries, and philosophical arguments about the nature of science as transcending human difference. But all of this is actually rooted in his religious beliefs. That is, he's a Quaker and a pacifist, and an internationalist along with that. And he's deeply concerned the way he sees science being, as he sees it, being destroyed by the war, as the international community of science was being shattered. So when Eddington gets this letter about relativity, he's excited not just about the theory because of its physical implications, but also because he sees this as a perfect example of why internationalism is so important. That is, if he, an English astronomer, can work with a German physicist to come up with this revolutionary new kind of theory, he can show all of his patriotic colleagues how dumb they've been since the start of the war. So he devotes the next few years of his life to becoming an expert in relativity and getting other people excited about it. And I want to stress for a moment that he has no contact with Einstein. Right? Because of the blockade, he cannot do so much as get one of Einstein's papers. He can get some fragmentary stuff from De Sitter, but occasionally their mail gets torpedoed as it's crossing the English Channel. So Eddington has to teach himself general relativity, and he ends up writing, say, the first textbook in English about it. But beyond just working on the science, he wants to get people excited about the idea of Einstein and relativity to show how important it is to keep paying attention to German theory, to international science as a whole. So one of the things he realizes that is going to be necessary for this is providing some kind of observational, empirical evidence that relativity is true, that it's not just this crazy idea. The next eclipse at which they could do the test was May of 1919, which was rather inconveniently across the southern hemisphere. It's not quite clear how the English astronomers are going to cross the U-boat blockade to get down to actually do the observation. But there's even deeper problems, which is that it's entirely possible Eddington is going to be in prison by the end of 1918. And the reason for that is that as a Quaker, he's refusing to fight in the war, and conscription is the law of the land. So after a great deal of religious protest and legal maneuvering, it seems that he is going to be arrested and put into one of these prison camps. But fortunately for him, and I recommend this strategy for everyone, one of his best friends is the most important scientist in the country, so work that out. Frank Dyson, the Astronomer Royal, manages to do some political maneuvering and get Eddington exempted from conscription on the condition that he go do the Einstein observation. So it works out quite well for everyone. So Eddington's not going to be in prison. There's a eclipse coming up at which they can do the test, but the war is still going on through 1918. It ends somewhat suddenly in November of 1918, and Einstein finds himself in the middle not of the imperial capital, but in the middle of the revolutionary capital. And it so happens that the first wave of the German Revolution in 1918 was a socialist one. So Einstein goes from being a political pariah to sort of the only reliable member of the German intelligentsia. And in fact, there's great stories of him negotiating with the revolutionaries who have taken the provost hostage at the university and such. He has a very good time, and he's greatly enjoying the fact that all of his enemies now are coming to him for help. So the war is over. Eddington's not in prison. They can actually do the expeditions to sea. They decide to send two. Eddington's team will go to Principe, which is this little island off the coast of Africa. A team from the Greenwich Observatory will go to Sobral in Brazil. It's a pretty good eclipse for doing the tests. The sun is right in front of the Hyades, so you've got lots of bright stars to test. It's particularly long, so you can get lots of photographs as well. So, as I've been trying to stress, Eddington is concerned not just to do the scientific measurement, but to make a big splash for this in sort of political and social terms as well. So one of the things he wants to do is go out and he's giving popular lectures, public addresses, writing magazine articles, getting people excited about the possible results from the expedition. And one of the things he's good at doing is framing the results in a particular way. So instead of saying we're just going to go out and measure and see if there's a deflection of light, he says we've got the Einstein prediction, 1.75 arc seconds, and then there's a Newtonian prediction, which is a different conception of the universe. Newton never predicted gravitational deflection, but you can do it, right? And then it's possible there's no deflection at all. So this is really a brilliant PR move, because now it's not just I'm going to go test a theory, it's a battle between two heavyweights. And Einstein is still obscure at this point, so he's been put on the level of Newton. So now it's a kind of title match that we get exciting to see. Two scientists enter, one scientist leaves.
It's not exactly a factor of 2.
It is not exactly a factor of 2. The story of why it's 0.83, I'm happy to tell, but it's lengthy. It involves Oliver Lodge. That helps. As the story goes, Cottingham is the assistant who's going to be traveling with Eddington to Africa. He's a clock maker. He doesn't know anything about relativity. Dyson is explaining the possible results to him, and Cottingham gets the idea in his head that the bigger the deflection, the better, right? Because we want Einstein, and Einstein's bigger than Newton. So Cottingham says, what happens if we get double the deflection? To which Dyson says, then Eddington will go mad and you'll have to go home alone. They do end up going. They travel south on what is essentially the first civilian shipping post-war. It takes them a few months to get down there, and give you a sense of what world travel was like in the wake of the war. Eddington ends up on Principe. It's about half the size of Manhattan. It's all chocolate plantations, and they set up here. And then over in Brazil, they actually bring two telescopes with them. The way you set up this kind of experiment is you put your telescopes horizontally for stability, and then there's a device in the front called a coelostat. It's a clockwork-driven mirror that tracks the sun through the eclipse. And then your photographic equipment is at the back there. The fact that they brought two telescopes turns out to be quite important. So like I said, a couple of months to get there, a couple of months to set up the equipment and get everything in place. And then on the day of the actual eclipse in May of 1919, one of the great ironies of being an eclipse observer is you don't actually get to watch the eclipse because you're working the machinery and the photography and such. So Eddington has this beautiful description of not seeing the actual eclipse, just listening to the metronome ticking off. The weather is actually not very good on Principe that day, so he telegraphs home through cloud, hopeful. Over in Brazil, the weather is perfect. They're very excited about the results they're going to get until the next day, when the Greenwich team starts developing the photographs. And they discover immediately, upon looking at the photographs before they do any measurements, that there was some optical problem with one of the telescopes, unfortunately with the bigger and more precise one. So they realized that immediately, 3 o'clock in the morning, that there was something wrong and a whole batch of the data is going to have to get thrown out. Fortunately, the other telescope brought back very good images. So this is one of the images from Brazil. These are the marks of the stars that they're going to be measuring the deflection on. And this is one of the photographs from Brazil as well. And Eddington is very excited to find out what the answer is going to be. So he does preliminary measurements and calculations in the field and decides that he did get some confirmation for the Einstein prediction. He later calls this the greatest moment of his life, when the new outlook of scientific thought must prevail, but never a one to let a joke pass. He then turns to Cottingham and says, "You won't have to go home alone." It takes months to get back to the UK. That was just Eddington kind of convincing himself. The actual measurement of data analysis, again, takes months of work. Eddington and Dyson decide to break up the work into two teams. So Eddington would take the photographs from Africa and do the work in Cambridge, and then Dyson would do the work on the Brazil plates in Greenwich. And that they would not communicate with each other during the whole analysis process, so there wouldn't be any kind of crosstalk or bias. And the results as they come out calculated are these. So this is Eddington's team from Africa, 1.61 arc seconds, plus or minus 0.3. And then the good telescope from Brazil is a little high for the Einstein prediction, but still, if you're thinking of it as Einstein versus Newton, that's clearly an Einstein one. And then there's this problem with the photographs that were clearly bad at the time. So what do you make of these? So Dyson's a thorough guy. He does all the measurements anyway, and finds that it's 0.93, which is sort of uncomfortably close to the Newtonian prediction, even though no one's really taking it seriously. And one of the things you can do when you get a field aberration like this is you just estimate what the field aberration is, and then you correct the measurements for that. And if he did that, he found it got up to 1.52, which is pretty, again, closer to the Einstein prediction. He thought that was too much intervention. That is, maybe that would not look sort of kosher to people watching. So he decides we'll just leave the crummy results in and let people make of them what they will.
So what's the relationship between the 1.98 and the 1.52 corrected?
Oh, so these are the two telescopes they had in Brazil. So these are all the photographs from one and the photographs from the other. The data also had a nice fit the 1 over r dependence that they were looking for quite nicely. Eddington is excited about that. And the point I want to stress but can't get into detail of here is that Eddington and Dyson spend an enormous amount of time thinking about the right way to process this data in the most transparent way, because they were conscious of the fact that Eddington was an Einstein proponent, and they were worried that that would look bad. So they spent a lot of time writing back and forth trying to prevent this problem and avoid it up front. Now Einstein is vaguely aware that all of this is happening. He's still under blockade in Germany. The war, there's an armistice on, but the war is technically still going until the Treaty of Versailles is signed. So Einstein is still starving and still not getting any communication. He knows there's an eclipse via talking to Lorentz, or there's an expedition. Once Eddington gets the results, he sends a telegram to Lorentz. Lorentz sends a telegram to Einstein saying that Eddington had found a confirmation for his theory. And Einstein is over the moon when he gets this telegram. He's so excited about it. He's been waiting for this for 10 years. And this telegram from Lorentz, he essentially shows to anyone who comes into the Einstein household over the next month or so. And he does things like he'll leave it on the kitchen table. And then when people come in, they say, "What's that?" And he says, "Oh, that's the confirmation of my theory." So there's a whole bunch of stories out there of people who happened to see this telegram at the time. My favorite one is this. One of his students comes in and looks at the telegram and she says, "How wonderful, this is almost the value you calculated." Quite unperturbed, he remarked, "I knew the theory is correct. Did you doubt it?" I answered, "No, of course not. But would you have said if there had been no confirmation like this?" He replied, "I would have to pity our dear God. The theory is correct all the same." So a lot of these stories have Einstein as the kind of too cool for school, like, "Oh, I don't care what the observers think. I just know that the theory is right." But in his personal correspondence, say this is the letter to Max Planck when he's talking about it, you can see how deeply moved he is and how deeply concerned he was to find this observational evidence for what he calls the beautiful, the true, and the real. The public announcement of the results doesn't happen until November of 1919, a full year after the war is over. Dyson organizes a special joint meeting of the Royal Society and the Royal Astronomical Society. Everybody's packed into this tiny little room. Dyson and Eddington also make sure there's members of the press there, that is, that they're journalists, which is a very unusual thing for a scientific announcement at the time. Everybody's very excited to be there. Again, remember, Eddington has been sort of prepping everyone for this dramatic moment for months and months by this point. One of the people in the audience was Alfred North Whitehead, who says it was like a Greek drama, and he describes the portrait of Newton looking down over the observers about to report the results. Dyson gets up and says, after careful study, there's no doubt that they confirm Einstein's prediction. That is, we have these two sets of good data that clearly confirm the Einstein prediction, and then this one set of crappy data that everyone is welcome to look at, but we're not going to take very seriously. J.J. Thomson is the president of the Royal Society. He's actually presiding over the meeting. He calls it one of the highest achievements in human thought. And the scientific community is agog over this. But then the lay public, that is the non-scientific community, gets very excited too, because those reporters at the meeting start writing articles like this: Revolution in Sciences at the Times of London the next day. Newtonian ideas overthrown. And these headlines spread around the world very, very quickly. This is the New York Times famous headline, Lights Askew in the Heavens. And Einstein is suddenly on the front page of newspapers all around the world. And I want to stress that this is weird. People do not know who Einstein is yet, okay? It's not a great achievement of the person who we already think is a genius. This is the second mention of Einstein in the New York Times ever. Okay. So he is a brand new figure breaking onto the scene. And one of the things that Eddington and Dyson work very hard to do is to make sure that the story of this as a great victory for internationalism in the wake of the war gets told that way. So Einstein is always described in these sorts of terms. He's a liberal, he wasn't in favor of the war, he rejected the patriotism of the other German scientists. And in fact, when Eddington and Einstein are finally able to communicate with each other, all they really want to talk about is this restoration of scientific internationalism. So proving the theory is great. Much more important is that we sort of preserve the nature of science despite the horrors of the war. This is Einstein's response to that. So this moment, when Einstein goes from sort of obscure academic to this triumphant figure of intellectual life at the worst moments in human history, literally coming out of the ashes of the war. This is when he becomes famous, right? So this is when what he calls the relativity circus. Everybody wants to take his picture, everybody wants to interview him. And he finds it all kind of faintly ridiculous. It's like this. He says, by an application of the theory of relativity, in Germany I am a German man of science, and in England I am a Swiss Jew. If I come to be represented as a bête noire, the descriptions will be reversed, and I shall become a Swiss Jew for the Germans and a German man of science for the English. So while he's celebrating the internationalism, he can't pass up an opportunity for a good joke. So this is the moment, I said, at which Einstein kind of goes overnight to being the scientific saint that we know him as today. And then the expedition itself kind of has a legacy. I think one of the important things about this story of how Einstein comes to be so famous is the importance of understanding the network that he's a part of. That is not just that he's a lone genius doing this work, but it is literally his close friends who he's happy to hang out with that make the observation possible and him to become famous. So the expedition itself. People often want to talk about the data from the expedition as its own kind of thing, and particularly this kind of concern of, was this good science? Was this a reliable, was it a good idea to believe in relativity in 1919? And people discuss the data right from the start. So right after the results are announced, Dyson makes copies of the photographic plates for anyone who wants them, so people do their own measurement and their own analysis of it. And by the middle of 1920, there's a straightforward consensus that the plates were analyzed correctly, and they did show the Einstein deflection. 2 years later, the Americans do their version of the expedition with much better precision, and it is presented as not supplanting the 1919 results, but confirming that they were done correctly. There's an important sort of conceptual legacy of 1919 via Karl Popper, the super influential philosopher of science. So Popper is a young man in 1919, and it's actually that event that gets him interested in science in the first place. And he decides that this is the model for how to do science, right? You have a theoretician who makes a daring prediction with a clear quantitative number, and then an observer goes out and checks to see if it is that then falsified. So when you hear about falsificationism, the idea that the nature of science is that its proof is wrong, that's via Popper, and that's because he thought the 1919 expedition was the perfect example of how to do that. And that's generally true for, I don't know, half a century or so. And then there's a handful of people, Shama in '69, Everett in 1980, who begin to suggest that maybe the 1919 results were not as reliable as everyone had thought. And in particular, that they said the error was very large, and maybe the analysis wasn't very good, maybe it didn't show what people had thought. It seems to me that it's not an accident that both of them are proposing new tests of general relativity at the time. That is, they're very concerned to convince everyone that the existing tests are not reliable, and now we should go do gravity probe B. But nonetheless, people are talking about this issue at the time. So the Einstein centenary in 1979, the RAS actually decides to pull the original plates from 1919 and remeasure them with the fancy electronic computers of 1979 to see what they can get. So they do this, and it turns out, so these are, it turns out Dyson's original analysis is this, the modern calculation brings us here. And then the corrupted photographs is the one where Dyson estimated he could have corrected it to 1.52 if he wanted. The computer comes up with essentially the same number too. So it sure looks like circa 1979 that the experiment was done well and analyzed correctly. But nonetheless, this general sort of mythology survives. It's kind of a water cooler thing, right? You talk with people while you're waiting for lunch. Oh yeah, didn't you hear that they messed up the data back in 1919? So it appears in print every now and then. Particularly influential, Hawking in 1988 has a reference to it. He has a new version of it in which he says that the data was unreliable because the error bars were bigger than the quantity they were trying to measure. You'll often hear that particular framework. This is not true at all. And in fact, the two astronomers who do the 1979 remeasure make a public statement saying that that's not correct whatsoever. The error bars were bigger than you might, it's not a 4 sigma measurement, but were just fine. But professional astronomers don't have much volume-wise to go over Stephen Hawking. So the legend kind of continues. In terms of intellectual, sort of in scholarly communities, one of the big moments is the publication of this book called The Golem, What Everyone Should Know About Science, published by two sociologists of science, Harry Collins and Trevor Pinch. And they have a chapter on the actually their very first chapter is on the 1919 eclipse expedition, and they're trying to make the case that science is just a social construction, that is data, physical measurements of the world generally are not what makes scientists change their mind about things, but rather their social and political commitments. So it's a strong argument attacking the reliability of the expeditions. Weirdly, they're actually drawing on an argument by two philosophers, John Ehrman and Clark Glymour, from 1980. And Ehrman and Glymour criticize Eddington because Eddington included that third group of data that was not so great. That is, they said, if you're really a good scientist, all data counts equally. That is, you can't cut out one set of data and say it was a bad measurement. So then Collins and Pinch run with this and say this clearly shows us that physicists just kind of make it up as they go. So nowadays, this is the version that you often hear. That is that Eddington included data that he should not have so as to make it look better for Einstein in the long run. David Merman writes a review of The Golem in which he criticizes Collins and Pinch's conclusion that science is just social construction, saying, of course scientists have social commitments and political ideas, but that doesn't mean that all the science they do is bad. So we need to have some balance of those things. And Dan Kennefic has also written a recent book on the on the eclipse expedition that particularly looks at the data analysis following on this idea. And Kennefic's argument is that, of course, Eddington and Dyson had to work hard to turn the raw data into something that was useful and persuasive. They had to make lots of decisions about what data was good and what data was bad. That does not mean that those decisions were bad. That is, we're always processing our data whenever we have to. So I like to think now, 101 years on from the expedition, that this is still a good model of how science works. Not because it's a purely rationalist one like Popper wanted it to be, or a purely social one like Collins and Pinch wanted it to be, but it's a good example of how people with strong political commitments and strong friendships can still do important science based on those ideas and ideals that teach us important things about the physical world. All right, thank you. I think I ran out of long.
So by Darwinian evolution, for any success story like that, there must be a huge number of bad stories that are not helping science.
Yes, that's definitely right. And I think that's right. People very often want it to be one way or the other, right? Like either you take everything or you get rid of everything. And I think what we have to do is actually look at the evidence at hand for the given stories, right? So sometimes political commitments are super important, right? If not for Eddington and Einstein's political beliefs, we would not have had a confirmation of general relativity in 1919. But at the same time, it's not hard to find examples in the very same year of people making terrible political decisions, terrible scientific decisions based on their political ideas. Things like Wilhelm Wien decides that he can't use any English terms in his science anymore. So that's right. So like thermodynamics, he says, cannot be used by German scientists.
It's Greek.
I know this is a great So yes, but what I want to say is that we can't make a blanket decision one way or the other. We need to actually look at what happened and make up our mind.
This idea of splitting up into teams is something that has worked well also more recently. But we did this, for example, in the Event Horizon Telescope because it seemed right to split up into 4 different teams to make images and then come together. But is there empirical evidence from behavioral studies that show, hey, if you split up into teams, you actually get the right result and you can have groupthink?
That is a really interesting question that I do not know. I don't know anything about the social psychology behind that. I don't know, because sometimes that can go wrong too, right? Then sometimes you get the effect where if you split into 5 groups and then 3 of the groups decide it's this, then the reflexes do this kind of voting kind of thing, which is not how science works especially well, right? So I don't know. I would have to ask a social scientist about this. I should say it's really hard to do multiple observations for things like this, if for no other reason than it's insanely expensive. So figuring out how to get 2 expeditions out of the money that they had was extremely difficult. So very often it's just like, let's just build one and be done with it, because we don't have the resources.
Couldn't they just have had a Zoom telecom?
That would have been really nice, actually. Actually, one of the interesting things about the story is, as you say, with the Event Horizon Telescope, it's all about coordinating the information, which is what they had to do here. But the speed of coordination was at the speed of telegraphs and steamships at the time. So seeing things fall together over the course of months, I think is one of the things that I find particularly fascinating about this story, is watching all the pieces come together.
People had time to think as a result.
Well, that's exactly right. So you're stuck on ships. Actually, there's lots of stories from this period of, like Chandrasekhar does his original calculations when he's stuck on a transatlantic liner for months at a time. And he's like, well, might as well do this numerical estimate that nobody would waste their time doing otherwise. So there's actually kind of a nice thing that comes with it. I'm sorry.
So we talk about how it was their political meanings and openness and sensitivity. But those 4 gentlemen in the picture, to what extent did they actually understand the theory of relativity?
These folks?
Yeah.
Well, I would say after Schwarzschild dies, I would put, and before Eddington masters it, De Sitter was probably the 2nd most competent person in relativity behind Einstein. Lorentz and Ehrenfest are interested in it, but they don't quite master the theory the way De Sitter does.
Yeah.
So I'd say they understand it very well.
So
Certainly.
the people who are playing an important part in politics to have it done didn't really. It's not as if they read the papers, understood them, or could tell that this was the right way to understand.
No, they certainly were. That's right.
They were.
Yes. Lorentz was, for instance, was definitely convinced that relativity was correct. And then the internationalism, they thought, well, we need the international structures to actually go out and convince people this is right. So none of these folks are blind sheep, as it were.
On this question of 2 teams analyzing data, we had the fairly recent thing, the Hubble constant being 50 or 90. And basically those 2 teams were analyzing mostly the same data and just kept pushing themselves farther and farther apart by how they edited and analyzed the data.
That's great. So was there a lesson from that?
try to be objective.
Data is not enough. That's
Yeah.
the.
Well, that's right. I think data is not enough is a good takeaway from, I don't know, most stories in the history of science, is that it takes work to turn data into something useful for thinking about. And you can actually see Eddington getting panicky during the whole time when he's not talking to Dyson, that he's made a mistake somewhere, and he's like, maybe I wanted Einstein to be true too much. And when he gets the first letter from Dyson saying, I agree that there's an Einstein deflection, Eddington is like, I'm so glad that that was the result, because as he puts it, he says, I couldn't see any way to make it be otherwise, right? I couldn't change it the other way from that. And Dyson wasn't so interested. It's just like, it's just an interesting scientific problem.
I mean, to the question that Shep asks, there are lots of examples of where you have a result in particle physics, and then other teams start getting the same result. So that it's compared to what, right? Separating the teams may not be a guarantor of total independence or absolute check, but having them done sequentially is certainly has not been historically a promising alternative to that. And there are lots of examples of that. The A2 split. There's the magnetic moment of the electron. I mean, there are all sorts of examples where someone gets a result and then other people start conforming to it, and you can graph that, see it very dramatically.
I think there's also a case where if you're left alone for too long with stuff, then self-doubt creeps in and you begin to agitate. And you can start with the right thing and then agitate yourself into a different local minimum and be like, well, maybe this is okay, And then,
Yeah, and I think you can actually see that with Einstein's theoretical work as he's finishing up GR, is that he doesn't have many people to talk to about this, right? So he can talk to his Dutch friends, he can talk to Schwarzschild before he dies, and then he can talk to Hilbert about this. But he doesn't really have any reason to think that they understand the theory any better than him. So he very often gets stuck in these cul-de-sacs. Like at one point he decides that covariance is not an important part of relativity, right? Which seems so absolutely bonkers to us today. But he had convinced himself, and he writes letters to Planck like saying, yeah, covariance totally didn't matter. And then eventually, actually, Lorentz sends him a letter, and he's like, you ever think about this? And it's like, oh, yeah, that's a good idea. Maybe I should work on that, and then that starts everything from there. Yeah, so I like the cul-de-sac metaphor. All right. All right. Thanks, everybody.